maggiorino piace.
So many upstairs, they're still in break.
Sì, ma che venivano stasera, sia Zumpano insieme a Calabria. Okay, so we will start in a little while, just waiting for one speaker. So you can have your seat. Okay, so welcome to our session, specifically considered, to present our project. The project is named, as you may see on the slide, is named RADIOAMICA. It means, it's an Italian acronym meaning radio, amica means friend, okay? So it's a kind of proposal that tries to, make radiomics more friendly from everybody, for all the partners, for all the parties involved in this radiomics process. Okay, so here we have all the partners of the project. I will introduce them in a little while. But first of all, I'd like to give you some information about the project, specifically what is the overall objective of the project. Okay? So the overall objective is pretty ambitious because this project was funded by the Ministry of Health. So it is a strategic project for Italy, for our country. So the objective is, as you may read, analysis, design, implementation, and validation of a platform that is intrinsically multi-institutional, and the platform is just called RADIOAMICA platform, for distributed, cooperative, and secure management of data models. It means diagnostic, prognostic, and predictive models, supporting therapeutic strategy with a main focus on the oncological context, based on radiomics and also radiogenomics. Okay, so this will be, more clear in a little while. And one of the focus, of the main focus of the project is related to artificial intelligence, because the call cited and mentioned specifically artificial intelligence. So in our project, we will use pretty sophisticated models related to artificial intelligence, specifically deep learning, but also techniques for explaining the results coming from such AI models, specifically XAI. And everything will be privacy preserved, in the sense that we will use sophisticated technique in order to guarantee the privacy, not only the privacy of the data, but also the privacy of the models that we obtain on the basis of the distributed data and sources. And we will have three important use cases, three important test beds, as you may see, related to important cancers like the breast, lung, and brain cancers. Okay? So just to give you some, let's say, pills related to what is radiomics. Okay? So for sure, you know what is radiomics, and there was this paper, very interesting paper, many 10 years ago, that was maybe the first inception of radiomics, named Radiomics images are more than pictures, they are data. Okay, so this is, you know, the inception, this was the inception of radiomics. Now, after 10 years, radiomics techniques are pretty sophisticated, even mature enough in order to provide more information, and this is, you know, another, let's say, hype about radiomics that is indeed not just a hype, but, you know, is something that currently is a reality about radiomics. So you can see here that images usually, according to conventional process, are analyzed, you know, by experts, you know, by doctors, experts in the specific analysis, the specific context, in this case, lung tumors, lung cancers. And of course, this is the traditional visual analysis. But if we dig into the images and we are able to extract quantitative biomarkers, then we could apply techniques, and we could be able to observe what it is impossible to observe using our eyes. Okay, so radiomics quantifying the invisible. Okay, so this is something that could strongly complement the traditional analysis. Okay, and the workflow of radiomics is the following. We start with a segmentation, so of course on the basis of images that we acquire using different techniques, as you may see, computed tomography, magnetic resonance, even PET, or many others. Okay, so in the project we also explore other ways to collect data. Okay, and I will be very fast here because, you know, the time is running. Then we have as a second step the features extraction. Of course, you know, there are many different features, and here the problem is also on the standardization of such features. Okay? In fact, in our project we have an institute, a national institute, focused on standardization, so metrological standardization. And of course, if we got a list of features, we need to select the feature using many different techniques. Of course, I will not go into details of the techniques available to select the features, but there are many of them, specifically in the radiomics setting. At the end of the day, we have to analyze. Okay, so we have to construct the model, then obtain the results and analyze what's going on. I would add also the explainable AI to this workflow that usually is not done. Okay? In the current radiomics workflow, the XAI, the explainable AI, is becoming, you know, to be included. And of course, the goal of the analysis is not only to use, you know, imaging biomarkers, but also to add multi-omics data. Then, you know, the transition from radiomics to radiogenomics to support what? As I told you, diagnosis, prognosis, therapeutical response, and the objective is to have medicine of precision and personalized medicine. So, very likely in the near future, our analysis will be based on non-invasive techniques. So we won't need, hopefully, to do some biopsy, okay, or just reduce, you know, the biopsy techniques to the minimum, and then we will use other techniques. This is our platform, so it's a big picture of our platform. You can see here that we will have multi-institutions, and in a little while we will discover which institutions, okay? And we have, so the edge nodes, each institution got an edge node, and then we have also the RADIOAMICA cloud in order to build, let's say, overall models, starting from the local ones. Okay? In an open, cooperative, distributed, privacy preservation way, and we will exploit federated learning, or at least techniques based on federated learning, in order to create this multi-institutional cooperative environment. Okay? Okay, we got the partners, and the partners are here, so in a little while they will deliver you, what they will do in the project. And the coordinator of the project is University of Calabria. I will be the scientific responsible of the project, but we also have the other two universities from Calabria, specifically University Magna Grecia of Catanzaro and University Mediterranea of Reggio. Okay? We have the most important hospitals of Calabria, specifically the one from Cosenza, two from Catanzaro, and the Metropolitan Hospital from Reggio Calabria. Okay? We included also very important healthcare research center, not from Calabria, but one from Rome, that is the IRCS Regina Elena, that is one of the most important, not only at the national level, focusing on different types of cancers. And also we have another IRCS, another healthcare research center named Monsino from Milan. Okay? Also focused on radiomics. So we have an expert of radiomics coming from Monsino and Polytechnic of Milan. And last but not least, we have also a national institute, specifically the National Institute for Meteorological Research, that is located in Turin. And this is fundamental for us in order to approach also at the end of the project, but also in itinerary, the standardization of our results. Okay? And this is the project organization. So you can see many different specific objects going from the development of the platform that is much more an ICT effort, okay? Data and knowledge representation, the construction of AI models. This is very interesting proposal. I was trying to say pretty innovative. This Radiomics virtual medical device. This will be led by Unica. I will tell you something in a little while. We also have a lab-on-chip device for liquid biopsy that is even pretty, cutting edge, and the 3 pilots. Another important aspect is the training aspect. So we aim to establish a postgraduate master, specifically in AI for radiogenomics and precision medicine. Okay, so not only scientific, results, but also we would like to transfer soon, during the project, we would like to transfer such results to the context in which we live. But not only Calabria, but all Italy. Okay, so in fact, the postgraduate will be an online one. So, doctors coming from all places of Italy, but even abroad, could participate to the postgraduate master. And just to give you a flavor, we will create such kind of environment, on top of which we will create a kind of layer for federated learning, and this environment will serve to all the other institutions, okay, in order to create models, in order to obtain distributed results, okay? And specifically, Unica will be focused on, from the experimental viewpoint, will be focused on the testbed related to the breast cancer. And we already have several results, specifically coming from the group by my colleague, Professor Costanzo. As you may see here, 2 important papers focused on the topics of the project. Okay, so we will start with our expertise. Okay, so we will not start by scratch. So we will start with our expertise, And we will put together in a coordinated way our expertise in order to create new knowledge, new results, impacting, hopefully, so this is our desiderata, to impact at the national level, okay? The healthcare system at the national level, okay? So, now I'd like to ask, the very first speaker after me from University of Reggio Calabria. Martina, please, you can have a seat here. So we start with Reggio Calabria. You can use this one. I will just
Professor Fortino said, my university is one of the partners of the project, and many labs of our university have been involved in our project. For instance, there is the lab for electromagnetic, the lab of telecommunication, the neurolab, the lab of electronics, macroelectronics, informatics, and last but not least, electrical and electronic measurements. I'm a member of the first lab, that is the lab for electromagnetic methodologies and application, which aims at binding together the knowledge on the electromagnetic theory to the one related to ICT framework. In particular, our main activities are about inverse problem for antenna synthesis and also imaging. So, in the framework of this project, I'm now just talk about the contribution of my lab, and in particular, my lab has been involved in the task entitled Radiomics Virtual Medical Device, which aims at not only consider the analysis of the data acquired by standard systems, but also it is focused on innovative and emerging techniques for cancer diagnosis. And so in particular, my lab, which has an expertise in inverse problem and imaging, will contribute to this task by introducing and performing a preliminary analysis about emerging techniques for the electrical properties tomography by means of the magnetic resonance. So the idea is the following. First of all, why we are interested in the electrical properties of the tissue. Because these electrical properties are relevant in diagnosis, because the human tissue can have different electrical properties depending on the typology, but also the physiopathological status of the tissue. So for instance, here we can see some plot that you can find on the literature, wherein there are the electrical properties that are the relative permittivity and electrical conductivity of healthy tissue and also cancer tissue, in particular for the breast. And we can see that each tissue has different electrical properties. So if we are able to retrieve the electrical properties of the human tissue, we can understand if this tissue is a tumor or is a healthy tissue. So in this respect, the permittivity and the conductivity could become a useful and quantitative biomarkers for cancer diagnosis, but also for therapy monitoring. So our contribution is to introduce to study an emerging techniques for retrieved electrical properties, and in particular we consider to use the magnetic resonance. We know that inside an MRI scanner usually it is generated a radio frequency field, but this field because of the interaction with the human body is perturbated, and this perturbation is related to the permittivity and conductivity of the tissue. So if we are able to measure the radio frequency field inside the scanner, we can retrieve the electrical property of the tissue, and so we can have some quantitative biomarker to discriminate the nature and the physiopathological status of the tissue. The idea underlying these techniques is that of retrieved electrical properties coming from the measurement of the radio frequency field inside an MRI scanner. However, underlying such reconstruction problem, there is an inverse problem, which is nonlinear, is imposed, its solution represents a very difficult task, and so the contribution of our labs is to introduce new techniques to solve such a problem. So, this is the end of my presentation, and this is the main contribution of my lab.
Okay, yeah, thank you very much for your presentation of the activities, at least the starting activities of your unit. So thanks a lot, and then I will invite University of Catanzaro, Magna Grecia, to come here. Okay, please.
Okay. Thank you very much, Giancarlo, and especially Virgi. And especially thank you for inviting us to join this exciting project. I will just briefly give a presentation of our activities, but first let me exploit this international venue to present my university. I'm from the University of Catanzaro. That is just on the other side of the region, if you can see the map, on the Ionian Sea. This is a mid-sized university for Italian standard, 12,000 students and about 300 faculties. And its characteristic is that it is focused on medical sciences. Biomedical sciences is the core business, both for research and education, and also clinical assistance, since the main flagship of our campus is the University Hospital. It is one of the 4 hospitals that contribute to the project. And the characteristic is that it is established in this new campus. It has less than 20 years, where the architecture of this campus reflects the concept, the initial concept of having a highly interdisciplinary research and education, where the hospital is connected to the research labs and to the teaching facilities. Here are the pillars of UMG unit, University Magna Grecia unit. Of course, the core of our unit is the oncology group that is led by Professor Tagliaferri and Professor Tassone. They have a great experience, of course, in the clinical care treatment of oncological patients. It's one of the main hubs for oncological patients treatment in Calabria. And they also have a considerable experience in conducting the clinical trials, clinical studies, with good clinical practice. And also they have a significant experience in drug development that derives from the translational oncology expertise, since they have studied a lot the role, in particular, of microRNAs on the development and on suppression of cancer. And this led to the development of a new drug that is currently under investigation in a phase 1 study. This led also our university to be the center for phase 1 studies. That is a good, very important achievement. So we are well settled from the oncological standpoint to deal with the topic of the project. But there are also other two important pillars. In particular, there is the one that is represented by the laboratories, biological laboratories that have very cutting-edge devices for dealing with all the different types of omics experiments. In particular, I have just put an example here that comes from the proteomics laboratory led by Professor Giancarlo. This is a very recent acquisition in his lab, and is a new device for targeted proteomics that will be very helpful in discovering new biomarkers. Okay. And then there is the third pillar that is represented by my group, the bioengineering group. We also have several research interests. One of these is certainly the medical image analysis. The expert in this field from our university is Professor Maria Francesca Spadella. And we have also a good knowledge of machine learning, deep learning, and computational biology and informatics. So these are all expertise that we will put and which will be useful to contribute in this project. In particular, here is Radiomics and Radiogenomics workflow. Giancarlo already mentioned some of the steps. Of course, the first step is the image acquisition, and we will acquire image from different devices, CT, PET, and others. And of course, the first step necessitates of a good preprocessing step for converting, denoising. Normalization, that is very important because for, in particular, some devices, it is very important to normalize images that come from multiple institutions, as we have seen, and other important processing steps. Then we have two ways, actually, that will be investigated. The first one is based on automatic tumor segmentation into D or 3D, and then on the so-called feature engineering step, where, of course, we have to find the significant features. So from the vast amount of features, we have to find the significant ones from the image, and that's the radiomics part. And then we have to join this with the search for biological features that we can find from omics experiments. So from genomics experiment, but also hopefully we will try to find biomarkers from proteomics experiment. And this is a way. Then when we have shrink down the available features to a significant number and relevant number, we try to find correlation by probing models and probing techniques with the outcome of the disease, that is mainly overall survival or progression-free survival, for example. But there is also an alternative way, as you can see here at the bottom, where the same image with the preprocessing step are fed into a deep learning algorithm. We have seen that one of the main goals of the project is to apply deep learning algorithms to the interpretation of these images. And the difference is that, as you can see here, you don't have a segmentation step. So you just give to the deep learning algorithm the whole image. This, of course, has pros and cons, because you can exploit the full power of, for example, convolutional networks. But on the other hand, it's less prone to explanation. And that is the other aim, Giancarlo talked about it, is to have an explainable protocol for analyzing the images, which is more simple, which is simpler with this other way. Now, with machine learning approach is simpler to have explainable results. But of course, we will investigate both. Okay, so this is very briefly our workflow that we will develop in cooperation, of course, with the other unit. And in particular, we will be focused on the pilot study on lung tumor. So these are the two main tasks, two main work packages. We call it OS, obiettivi specifici, so specific objectives in the project. In particular, UNG will be the leader for OS 7, where the activities are patient data acquisition, cooperative construction of diagnostic models, cooperative validation of collected data, and then the identification of predictive models to support therapeutic strategy. And then UNG will also lead the OS 9, that is the training work package, where we will contribute in establishing the master of second level in artificial intelligence for radiogenomics and precision medicine. And we also set up lab activities and internships based on the RADIOAMICA platform that will be exploited by medical students, in particular the students of the degree in medicine and digital technologies. So this is very briefly the sketch of our activities. Thank you again.
Okay, thank you very much for this outlook of the activities of the University of Magna Grecia in Catanzaro. Now we will have some contribution, pre-recorded contribution, specifically from the Healthcare Research Center, Monzino and Regina Elena in Rome, Monzino in Milan. Okay, so I will play back the videos they sent me. Okay.
Good morning. Thanks, Professor Fortino, for inviting me to speak in this meeting. So, genomic alterations in gliomas are associated with a number of radiographic features on MRI. It is possible to demonstrate this correlation using morphological sequences ST2 and FLAIR, non-morphological sequences as diffusion, perfusion and spectroscopy, and the new techniques as radiomics and radiogenomics, machine learning, deep learning and artificial intelligence. We could use this association in cases of unresectable lesions in eloquent locations, in patients who cannot be operated on for medical problems, or in stereotactic guided needle biopsy may not always reflect the phenotype of the whole tumor. This slide shows a previous experience in collaboration between University La Sapienza and Regina Elena National Cancer Institute in Rome. In the first work, our aim was to develop a deep learning model for IDH prediction on multiparametric MRI with an accuracy of 83% using a perfusion technique and relative cerebral blood volume images. In the second work, we aimed to compare machine learning to predict clinically relevant tasks for high-grade gliomas as overall survival, IDH mutation, MGMT promoter methylation, AGFR amplification, and Ki-6070 expression with highest accuracy. So, in the pilot of the radiogenomic brain tumors, we will use MRI with morphological sequences T2 and FLAIR and advanced techniques, diffusion that permits to obtain some information about cellularity of the lesions, and perfusion about neovascularization. When we use these techniques, it's possible to obtain qualitative and quantitative data and liquid biopsy. This is an example we have two lesions with similar signal intensity on flare sequences, but different on diffusion and perfusion, because the first lesion has higher ADC as lower cellular density, and lower perfusion parameters such as permeability and blood volume as lower vascularity, has possible low-grade gliomas. At surgery, the first lesion was low-grade gliomas and the second lesion high-grade gliomas. So, the goal one of this pilot is to carry out a stability study of the radiomics features with respect to the main parameters of the MRI sequences through the use of a phantom for radiomics analysis. The second goal is to build models based on pre-surgically radiomic features with the aim of predicting ADH1 mutation, MGMT promoter methylation, ATRX mutation to stratify patients in risk categories. So, key performance indicators could be the improvement of progression-free survival and overall survival in relation to the possibility to differential diagnosis between pseudoprogression, radionecrosis, and relapse, with consequence earlier identification of the relapse, which would allow to optimize the timing for the treatment. And also, it's possible that the therapies can modify the molecular profile of brain tumors, and for this reason, we think that these changes can be defined by a combination of radiomics and liquid biopsy. So, thanks for your attention.
Okay, so this is the contribution from Regina Elena in Rome, and as you may know, they got a lot of data, on which we can, in a distributed way, we can perform our, create our models and perform our analysis. So it is a strategic healthcare research center, and using our RADIOAMICA platform, we will be able, to put such data in sharing with all the other institutions by preserving the privacy, by saving network resources and constructing models at the global level. Okay, so this is something that federated learning is able to support, but indeed this could be also a very interesting large-scale platform on which to understand many things, not only from the medical viewpoint, but also from the ICT viewpoint. Okay, so this is will be a great experiment at the national level. Our idea is also to try to share our results at the international one. So maybe after the project, we will welcome other institutions at the European level, for example, starting from the European level, to join the platform. And this could be a great plus for us at the national level, but also at the international one. Okay? Now we will have another video from Monsino in Milan. Okay? Specifically our colleague Valentina Corino.
Good morning, everyone. I'm Valentina Corino. I'm affiliated both with Centro Cardiologico Monzino and Politecnico di Milano. And I'm very happy to be here, even if virtually, to be part of this special session on RADIOAMICA project. And in this brief talk, I will describe the methodological steps that we will perform in the project. There are two main blocks. The first one is the radiomic feature extraction that is divided into 4 sub-blocks. The first one is image segmentation. That means the identification of the region of interest that contains the main tumor. Then we have image preprocessing, that goes from image standardization to voxel size resampling in order to have an isotropic resolution. Usually we use 3 millimeters as resolution. Then we have feature extraction that will be performed by Radiomics, that is an open source platform for the extraction of radiomic features. And features can be extracted from the original images, or actually volumes, and on a filtered version of it, obtained, for example, using the wavelet filter or Fourier transform and others. With Radiomics, we will extract 851 radiomic features from each image that are divided into different classes. We have first order statistics that describes the gray level distribution of the voxel. Then we have a descriptor of shape and size of the region of interest. And then we have features derived from matrices, 5 different matrices that you see listed there, describing the texture of the region of interest. And finally, all these features will undergo zeta score normalization before entering the classifiers, for example. The second block is radiomic feature selection, and the very preliminary step in this block is the identification of stable and discriminant features. What do we mean? We want our feature to be stable. This means that if we slightly move the ROI, the region of interest, from the blue one, for example, to the green one in this panel A, and we compute the features, we want them to be very similar to each other. This mimics different segmentation, for example, performed by the radiologist. Not only, we also want our features to be discriminant. This means that if we consider a completely different region of interest that does not contain the tumor, as the green region of interest here in panel B, we want the features in this region to be very different from the ones computed in the tumor volume here. So, to perform this very important and preliminary step, we have developed a methods based on geometrical transformation of the region of interest and evaluation of the features by means of the interclass correlation coefficient. So after this step, we will have a subset of features that will be stable and discriminant. The second step is the evaluation of non-redundant features, and this will be done by the correlation coefficient. This simply means that if 2 features are highly correlated, where with highly I mean their correlation is higher than a certain threshold that usually is 80–85%, one of these 2 features will be discarded. And finally, we will perform feature selection to have a dimensionality reduction of our problem to identify the more relevant features. And this might be done with different techniques depending on the problem. This is all for my brief talk. Thank you again very much.
Okay, great. So, as as you may see, also, the Monzino research unit is pretty focused on radiomics. Already they performed a lot of research in this direction, so they will be the supporting partners for all the projects. Now we will conclude with the National Meteorological Institute in Turin.
Good morning, everyone. My name is Angelo Angelini. I'm a researcher at INRIM, the National Institute of Meteorological Research. And today I would like to explain what is the role of INRIM in the RADIOAMICA project, and especially concerning the data standardization and methodology for machine learning. Before going to the point, I want to introduce a bit what is INRIM, because maybe someone of you is not so familiar with it. INRIM is a public research center, and it's the Italian National Meteorology Institute, which means that INRIM realizes the standards and the reference standards of measurement units of the international system, and thanks to this standard, the Institute ensures measurements that are reliable and comparable on both a national and international scale. And indeed, it is including European network, which is EUROMET, which is the European Association of National Meteorology Institutes. And in the last years, EUROMET has been challenged by the many changes in science and meteorology, and in particular by digital transformation. And indeed, a few years ago, there was in this nature, some researchers stated that quantifying uncertainty in complex problems is almost becoming a field in itself. What this means that when you have complex algorithms processing huge amount of data, it is not trivial to understand what is the uncertainty associated with the outcome, and what is how to quantify the uncertainty. And in this context, it has been founded a project which is MathMet, which actually deals with this problem. So this is an European roadmap for metrology in artificial intelligence and machine learning. And the goal of MathMet is to ensure that quality and trust in algorithms, software, tools, and data for metrology and inferences made from such data. So this is quite an important topic, and key points have been identified in this roadmap. The first one is the uncertainty quantification, which is, so we need to give a quantitative assessment of uncertainty to evaluate the quality of predictions, to understand how good is the outcome of a model in a quantitative way. The second key point is generalizability and robustness. So how well the algorithm applies to new data, and how robust is it to data perturbations, for example, to noise in data. The third is interpretation, which means that the algorithm cannot be a complete black box to us, but we have to be able to understand the predictions in terms of underlying physical effects that are known. And the third is the quality framework. And this has to do with the standardization of data, because choice and quality of data is critical to the performances of the model. So in order to explain to you what is the role of INRIM in the RADIOAMICA project, I can show you what are we working on in our group, especially Dr. Gianluca Milano, Dr. Federico Ferrarese Lupi, and PhD student Chiara Magosso, which recently joined our group. So in our group, we are mostly focused on material science, and in material science, we have a lot of different characterization techniques that provide data in different formats: images, spectrum, data, Fourier transform data, and so the goal of the project that Chiara Magosso is working on is the creation of a framework for standardization of digital data. So how to put together all these informations and have a database that can be given to a model that can, for example, predict the outcome of some fabrication techniques. So the problem is not trivial, and the key point is that every image, every result of characterization needs to be accompanied by metadata. What are metadata is everything that is behind the image. So, for example, the process parameters, the outcome of the analysis, the image parameters, and all this data have to be put behind the image in order to make the image comparable to similar images or images taken from similar instruments or data taken from completely different systems in completely different conditions. And so it's a standard way to have this metadata in such a way that an algorithm can elaborate them and then to make some to work on the algorithm that processes the data and the metadata. So with this, and I believe that this process is quite general and it can be applied to other completely different characterization of diagnostic tools or characterization techniques or diagnostic tools. And with this, I want to thank you for your attention and hope to see you soon in presence.
Okay, so also let's thank Angelini, Dr. Angelini, and the Institute. As you saw, the approach, the standardization approach is fundamental, and in my opinion, it should be put, in operation in itinerary, not just at the end of the project. Okay, so maybe some choices could be driven by some standardization efforts at the international level. Okay, this could be, in my opinion, important apart from the scientific aspects. Okay, so we are concluding. We just have a couple of minutes. So I'd like to also invite Marcello, who would like to say something. Because this project was, let's say, concerted also with you, with your group. So if you would like to add something from the audience, please.
Just some words. Many thanks to Giancarlo for the interesting project that we are involved. I would like to thank all of you to stay here. In particular, I would like a colleague from the Annunziata Hospital, Dr. that we work on the pilot of breast cancer, but also the other colleagues of the University of Calabria that we already are involved in some interesting projects related to the role of imaging in the diagnostic and therapeutic novel perspectives in breast cancer in particular. So we are very happy to work on this project. And this is also a pioneer project for us to take some new links between the medical area in our university and the ICT area in the University of Calabria. So we will hope that in the next future we present soon the results of our work. We aim to achieve some good results to contribute to the medical field in our region and also in the national healthcare of Italy. So we hope to stay here again in a next meeting organized by our good coordinator, Giancarlo, and to present the results of our work. Thank you very much.
Thank you, Marcello, and I'd like to, conclude this presentation in order to start also the advertising, the project. Because another important point will be that we will aim to build a Radiomics, Radiogenomics lab at University of Calabria. So this will be also another important outcome of the project. So as Marcello said, we will see you very likely in the near future, okay? And we will provide additional let's say, information about our project. And any question, please offline, because we have to cut the session, because there is another session that is coming. So anyway, try to be close to us in order to ask additional question, clarification, hopefully, let's say, even interaction and cooperation, because there are other projects, including the same call, funded in the same call. One is over there, and maybe we can find some synergy between the projects. So we will have anyway a discussion, and we will be in the same direction with many different interactions, as in the European Horizon Europe project, in which they create ecosystems. So we will try to create ecosystem using a bottom-up approach. That is, in my opinion, the best one. Okay, thank you very much, and see you soon.